Okay, so I'm going to try to keep today's lecture a little shorter than yesterday's lecture, in part to make up for the fact that yesterday's lecture was an hour of my dull droning monotone. So, as promised, off to a great start. As promised, today's lecture is on Compton scattering. Um, and so I alluded to this in yesterday's lecture, but the basic idea is we are scattering light from electrons. And so I wanted to start by what we expect classically, because I listed this as one of the problems that classical physics would have. And so imagine that you have an electromagnetic wave approaching an electron, and the electric field is going to cause the electron to oscillate uh, parallel to the electric field. And classically, you expect it to provide energy that could send the electron uh, jostling forwards, and it will scatter the uh, the the electromagnetic wave so that if it had some initial frequency and wavelength f naught lambda naught, it scatters at some angle theta with some new frequency and wavelength f prime and lambda prime that, owed to statistical mechanics, could take on effectively uh, an incredibly wide range of values. So classically, um, wave comes in, electron gets pushed forwards, oscillates, owed to the electric field. The wave scatters with some new frequency and wavelength f prime lambda prime that uh, that are not pinned, that can take on a large spectral range of frequencies and wavelengths. When Compton actually carries out this experiment, uh, that's not what he finds. What he finds is that uh, for a given scattering angle theta, there is one allowed uh, scattered wavelength, and that isn't entirely understood classically. And so I'm going to give you a rough derivation of this using using some of our 20th century physics. So first, I want to point out that uh, uh, incoming photon, I didn't actually draw this as a photon, so maybe I should take a second pass at this. So my usual pictogram will be as such for a photon, um, and so you can imagine the photon comes in, strikes the electron gets scattered off at some angle phi with respect to the original path, and then the photon, with some uh, changes to it, follows this new path theta. Um, I'm I'm going to draw this as a wave just because I think it's simpler. But remember, the interaction with matter, it tends to display particle properties. But here it's traveling and here it's traveling, so let's consider its wave properties for a while. So with that said, uh, the the recoiling electron, the electron gets flung um, far away at some new angle phi. It has some momentum, as we saw at the end of our discussion of special relativity, uh, uh, p, that should be a lowercase e, um, p for the momentum is 1 over c times the square root of e squared minus e r squared. Sorry, I'll probably catch a few more of those as I go along. I want to call this our rest energy squared. And I think in our last lecture I used e sub r, and so I want to try and be consistent. But it's hard for me to remember to do that because that's not the terminology I learned with, but I think it's what your book uses. So the momentum of the electron is just 1 over c times the square root of e squared minus er squared. And again, h over mec, h Planck's constant 6.626 times 10 to the minus 34 joule seconds, mass of the electron 9.11 times 10 to the minus 31 kilograms, c the speed of light 3 times 10 to the 8 meters per second. If you take h over mec and report it in nanometers, you get 0.00243 nanometers. So I want to look at this this interaction, and remember when we were talking about relativity, we were saying that the photon carries momentum. It doesn't have mass, but somehow it carries momentum. Well, this is the original photon's momentum, right? So it's directed, it's a vector, right? So it's directed along the original path of the photon. The scattered photon has momentum in this direction, right, at some angle theta with respect to the original direction. Yay? And note that the recoiling electron is scattered phi, angle phi above the horizontal, right? And so the momentum of the electron is directed phi. I can draw this as a closed triangle because I believe in conservation of momentum, right? And so, so the momentum of the scattered photon plus the momentum of the electron needs to equal the momentum of the original photon. These two lower vectors have to sum to this upper photon momentum vector. Hopefully that's all right. So now I want to return to our relativistic definitions, and if you need a reminder of this, it's probably a couple videos back at this point, but it's also in your notes, I'm sure. We said that the energy of the photon went as p times c, right? And so the momentum of the instant photon is just the energy of the instant photon over c. But we also have this Einstein definition that the energy of the photon is hf. And so we could also write f is equal to c over lambda. And so that allows us to say that the momentum of the photon is just h, Planck's constant, over lambda. And again, I recognize that when we're speaking of photons, this is a little weird because the photon doesn't have a wavelength. And yet we're saying that it also remembers that it's a wave. And so the momentum is h over lambda. So the instant photon has momentum h over lambda I, whatever the instant wavelength was. The scattered photon's momentum will go similarly as h over lambda 2, or lambda prime. And remember, our little triangle here just says that the instant photon's momentum needs to equal the scattered photon's momentum plus the electron's momentum. We can use law of cosines here to say that uh, that the square of the electron's momentum is equal to p instant squared plus p scattered squared minus 2 times the dot product of those two momentum, or that the square of the electron's momentum is p1 squared plus p2 squared minus 2 magnitude p1 magnitude p2 cosine of the angle between them. I'm going to call that equation 1. All this is the law of cosines. So hopefully you're okay with that. If you're not, hopefully you have a math textbook nearby or Google at hand. We could also, so in some sense, this is just a statement of our conservation of momentum, right? That this just stems from this statement. We could also try to conserve energy. And so coming back to our original statement, we have the energy of the photon instant, and the electron is originally at rest, right? And so P1C, that's the energy of the instant photon. ER is just the rest energy of the electron. So we're going to jump into a frame where the electron is at rest with respect to us. And so the energy before the collision is just the rest energy of the electron plus whatever energy the light carried. Yay? After the collision, we have some new energy for the light, and we have the total energy for the electron. So it still has its rest energy. It now also has some energy associated with its motion, and so we can say that the total energy. Remember the triangle that we had examined previously, where we said that the rest energy was one leg, PC was a perpendicular leg, and the total energy was the uh, the energy of the object. I've replicated. I've tried to. I really have tried. I've replicated it here for you. That PC was one leg, MC squared, which is your rest energy, is another leg, and E is the hypotenuse. So we have that E squared is PC squared, P squared C squared plus ER squared. And so if I just want E, it's quantity PC and quantity squared plus ER squared all under the radical, which is what this is, right? This is just that guy. So this is our statement of conservation of momentum. This is our statement of conservation of energy. We can square, well, actually, first let's bring this to this side, right? Bring P2C over to the left side, so that we get C times quantity P1 minus P2. And now let's square both sides. So we'll get an ER squared term. We'll get C squared times quantity P1 minus P2 and quantity squared term. And then we'll get ER times C times quantity P1 minus P2 and quantity times 2 term. right? Uh, so all we did here is first bring this to this side by subtraction, and then square both sides. On the right side, all that would remain is this, so when we square it, it just becomes ER squared plus uh, P squared C squared for the electron. Hopefully that's all right. Convince yourself that you can go from here to here. We can then solve this equation for PE squared. And if you do that, you should get something like this. And I'm going to call that equation 2. Hopefully that's not terrible. Then if we take equation 1 and equation 2, set them equal to each other, right? Because they're both momentum of the electron squared, right? Set them equal to each other. Nice things happen. First, they both have p1 squared plus p2 squared, and so those terms cancel. And so we can get that ER over C times quantity P1 minus P2 and quantity is equal to P1 times P2 times quantity 1 minus cosine of theta. And so take this and this, set them equal, convince yourself that you can get to here. And let's take this equation and multiply through by HC over P1, P2, ER. And so if we multiply through by HC over P1, P2, ER, so multiply both sides of this equation by this, we get this and this, right? Note that the C's cancel on the left, so do the ERs, so that we're left with, in the numerator, H times quantity P1 minus P2. In the denominator, we're left with P1 times P2. On the right side, note that the P1, P2 cancel, so that we're left with 1 minus cosine theta HC over ER. Note that we can write the left side of this, H times quantity P1 minus P2 and quantity over P1, P2 as just H times quantity 1 minus P2, 1 over P, let me start again. We can rewrite H times quantity P1 minus P2 and quantity over P1, P2 as H times the quantity 1 over P2 minus 1 over P1 and quantity. And that's still equal to the right side of this equation, right? But now if we recall that lambda is h over p, that was something we got way back here, right? If we recall that lambda is h over p, well, here we have h over p2 minus h over p1. That's the same as lambda 2 minus lambda 1 on the left side is still equal to HC over ER times 1 minus cosine theta. But now let's just remind ourselves that ER, the rest energy of the electron, can be written as mass of the electron times c squared, so that we get to HC c over mc squared, 1 minus cosine theta, which at long last we can cancel one of those c's to get that lambda 2 minus lambda 1 is h over mass of the electron times c times quantity 1 minus cosine theta and quantity, which, note, is what the Compton scattering results of experiment showed. So again, h is 6.626 times 10 to the minus 34 joule seconds. The mass of the electron, 9.11 times 10 to the minus 31 kilograms. The speed of light, 3 times 10 to the 8 meters per second. 1 minus cosine theta, right? And so the difference between the scattered wavelength and the original wavelength goes as h over mec times quantity 1 minus cosine theta. Hopefully this isn't too terrible. Our lab next week actually is our experimental effort to look at the Compton scattering. So so I think that you'll have some fun with that one. Hopefully this made sense. If not, then please reach out to me and let me know, and I will try and make it make more sense. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your day, but not so much that I won't see you tomorrow.